Good evening, everyone. I think we have a lot in common. We all remember that when we were children, it took a very long time for Christmas to arrive. Imogen, I'm sure you still think it takes a long time for Christmas to come. But I tell you, once you are old like myself, a year passes before you feel it has even started. Now, in spite of that, I think we agree this must be an illusion, and there must be some sort of a real time, the sort of time that is shown right here, which is the same on everyone's phone. So despite our perception that time can sometimes change and morph, I think we can agree that there must be, in some physical sense, clocks that show the time in an agreeable sense. And likewise, there are rulers that have lengths that we can agree upon. And having rulers and clocks, you can then measure speeds as the amount of time traveled per, amount of space traveled per unit time. For instance, let's look at this car. This car travels 100 kilometers an hour. That means 100 kilometers in space per 1 hour in time. And another one's coming towards it at the same speed. Now, here is a question for you. If the left car measures the speed of the right car coming towards it, or this car measures how fast the other one's coming towards it, what would they measure? Well, you would think, surely that must be 200. You just add up the 200. Now, turns out that if you measure this to unbelievable accuracy with all the full physics gear in a physics lab, what you find is this number. Not quite 200. Now, of course, you have to make sure that your measurement is accurate enough to all these digits. But if you get it right, that's what you find. It's not 200. All right, so why bother? You may as well say that's close enough to 200. No, let's keep drinking wine and end the evening here. It certainly is good enough to give you a speeding fine. But here's the thing in physics. If there is a difference between your theoretical prediction and what you measure, no matter how small that difference is, if it's not explainable by measurement error, then your theory must be wrong. Okay, so something is wrong about the way we think about speeds. And if something is wrong, then it may very well be that there are other situations where the error is much worse. For instance, if you were to replace this car by a really fast car, say, let's go crazy and replace it by a source of light. Now, the light's coming at this speed. That is the speed of light that you measure relative to the ground, about 1 billion kilometers an hour. I don't want to write this number every time, so I'm going to call it c. That's from now on the speed of light. And now, if this car is coming towards it at 100 kilometers an hour, how fast is he or she going to see that light hitting the car? Is it c plus 100 kilometers an hour, as you would expect? No. It's just straight up C, okay? So here things start going wild, okay? Just think about this. You know, if I have a laser pointer that's sending out these nice little blue particles of light, it takes about a nanosecond from here to get to there. So I press the button, a nanosecond later, the particles hit my hand at the speed of light. And you would think, surely, if I go like this, then the particles hit my hand a little bit faster if I come towards those particles. But no, that's not what you measure. And because speed is just measured as distance per time, something must be wrong about the way we intuitively think about space and time. Somehow, time must be different in the moving car, and perhaps lengths must be different in the moving car than for the observer outside the car. It's got nothing to do with the car. You can run, or you can take a plane, you can do whatever you want. It's about the motion. So that's the basis. And it really took Einstein and Hendrik Lorentz, a Dutch physicist, to figure out what's truly going on there. This is a picture taken in Leiden, a Dutch university town, where these two met and regularly worked together. And what they found explicitly is that if the two cars are at rest, not moving at all, they can have clocks, and these clocks will go exactly at the same rhythm. And they can have rulers, and these rulers they can both have a ruler of the same length, and they will both agree that these rulers both have the same length. Now, as soon as they start moving, they do not agree anymore on the clocks. Okay? They go differently. Neither do they agree on the length of a ruler. And to make things even worse, a little bit of this one's space appears as time to this person, and vice versa, and the other way across as well. Okay? A really strange thing is taking place. Time becomes space for a moving observer, and vice versa. That's where you cannot imagine things anymore. You can write down the equations. It all works out really well. So in what sense do the clocks change? Well, this one will see that the other one's clock is ticking slower. But this one will see that this clock is ticking slower. Okay? It's completely symmetrical. Both are moving relative to each other. They both find the other one's clock has slowed down. Likewise, they will both see that the other one's ruler has been compressed. This is the theory of special relativity. And just to celebrate this particular finding, Leiden has chosen to make this nice mural where they drew this ball, and that's supposed to be a round spherical ball at rest. And now this ball is moving, and as it moves, it becomes compressed. And nothing to do with air drag or so. This is in a vacuum. The ball gets compressed just because of the relative speed to the observer. It is not compressed for the person that travels with it. Okay? It's an effect of changing space and time. Now, why don't we observe these things in everyday life? Why don't all our iPhones show a slightly different time? Because you have to travel at horrendous speeds, near the speed of light, for this to become noticeable. So we haven't really developed any intuition for this at all. But that's really what's taking place. And I think we can do better than this mural, because here is only shown the length contraction. With it goes a change of time. And so I thought it'd be nice to add little clock faces to these circles, and that's shown in this video. Well, this is the clock seen by the observer at rest. And then as soon as you start moving or the ball starts moving, doesn't matter, it's all about the relative speed, the moving clock slows down. So that's, in a nutshell, the theory of special relativity for you tonight. Now, what has that got to do with black holes? Black holes are all about space and time, but they're also about gravity. So somehow, we now have to marry this new concept of space and time that can morph and so on with the concept of gravity. And before we do this, let's just go back to basic gravity. The first solid mathematical theory of gravity goes back to Isaac Newton. It was him, who famously came up with this nice, beautiful equation that describes the straight fall of the apple as well as the circular or elliptical motion of the moon and the planets and the stars around the galaxy. So all in one single equation, he managed to describe these straight orbits and the non-straight orbits and the ones that change the speed and the ones that keep the speed. It's the same physics applied to different settings. It's really the first one to come up with such a model. And it's an extremely good model, unbelievably good. It is beautiful mathematically, but also it solves almost every problem on Earth to do with gravity. We can easily build cars and rockets and planes using Newtonian physics. We can easily fly to the moon using Newtonian physics. We can fly to other planets using Newtonian physics. We can predict lunar eclipses like the one last night using Newtonian physics. It works unbelievably well. But there's one sort of funny thing or one little unsatisfying thing in Newton's theory. And explain you now what that is. Here's a little person who is throwing a ball, standing on the ground, and of course that ball falls down rather quickly because that person throws about as well as me. So it lands on the floor. Now, we could have put a box around that person, a box that is completely tight, it's a prison, you can't see what's outside. And you can ask the question, could that person in that box still know that the box is on a planet rather than, say, in space or so? And of course, the answer is yes, because you can still throw the ball and the ball will fall down, and so you know has to be a planet underneath that pulls the ball down. Except somebody might, while you were asleep, have put that box on a rocket ship and taken you far away from Earth, where there's no more gravity from Earth, and then accelerated the rocket by using the thrusters at a constant acceleration. When you accelerate the rocket, you get pressed down in that rocket, and you can actually tune the acceleration in such a way that the effect, the force you will feel in there is exactly the same as standing on a planet. And for the person in that room, it would be absolutely impossible to tell if they are in that room or in that room. The ball will fall exactly the same. But worse, any possible physics experiment that you can conceive of will be exactly the same. Play with water fountains. You can have fire. You can have magnetic fields. You can have nuclear physics. Whatever has a gravitational component to it will be exactly the same here as there. So it appears as if those two things are completely equivalent. Okay? That's called the equivalence principle in physics. And you really have to wonder if two phenomena appear to be exactly the same by any observable account. Are they not truly the same? In other words, is gravity not truly just acceleration? Now, of course, in Newtonian physics, it isn't, and I'll show you how they differ. So let's look at the rocket, and let's do a little diagram here. I plot here the height of the rocket, so compared to some floor. And of course, because it's flying up, it will go up. So this is time here. As time goes on, the rocket goes up. Now, if it was flying without accelerating, this would be a straight line up. But since it's accelerating, the speed increases. And so this line gets up steeper and steeper, okay? Called a curved line. And it's because of this curvature that the person inside the cabin feels that inertial force that pulls the person down. Okay? If you didn't have any acceleration, if the rocket was turned off, the person would be floating in microgravity. But if you are accelerating, and that makes this line curved, well, then you feel the inertial force. All right, that's the description of an accelerating person, accelerated person. Now, the other person, on the other hand, can plot the same diagram. What you see here is, again, the height above ground against time. And of course, the box just stays on the ground, so the person's height doesn't ever change. It's just a flat line. And you explain the being pulled down by this force called gravity. Right? See, these are two completely different pictures. That's how Newton saw them. And Einstein was thinking, how can I possibly, make these two things appear the same thing in the theory? And he said, how about this? We forget about gravity. There's no such thing as gravity, but instead, this sheet here is not flat. It's just curved. Okay? Space-time itself has some curvature. Very hard to imagine what that means, but we can, again, write down the sort of equations that would describe such a space-time sheet. And the idea is that because this whole screen is now curved, that line is curved as well, exactly the same way as this line is curved. All right? That's how you put gravity and acceleration on the same theoretical footing. Okay? I know there's a lot of theory. This was not going to be an easy night by all means. The way you then represent gravity, say, around the Earth is by having this mesh that moves as time goes on, because the mesh should represent space, and then as time goes on, you see that mesh change because the mesh is curved in time. And so when you look at different times, you see a different mesh. And now the apples that fall down, they don't fall down due to gravity, but because they want to stay at the same spot on the mesh. So they are not really moving with respect to that space-time, or they are moving in a very, very, very simple way. And then once they hit the ground, then they feel the force of the Earth that avoids them getting to the center of the Earth, right? Now, it's nice to draw these pictures and so on. I mean, that's the sort of thing that a philosopher could easily do. But then the hard thing is to now come up with the, nothing against philosophers by all means, but the challenge here is to write down the sort of equations that make predictions that you can then test. Predictions that are different from Newtonian gravity. That's what you want to do, and that's, of course, what Einstein did. And here is the equation. Now, of course, we're not going to go through that equation, but the important thing is this little equal sign here, and then there's a left hand and a right hand. Everything that's written on the right hand, this thing here, describes the motion of the object. For instance, the motion of the apple, okay? And its mass. Everything on this side describes the shape of space and time. So what this equation does for you, it tells, well, matter tells space-time how to curve. And if you read it the other way, then the curved space-time tells matter how to move. Okay, that's this beautiful theory of general relativity in 2 simple sentences. Now, this equation looks a little bit funny in its font up there because it's part of another mural in Leiden, would you believe? Where they've put down that equation for everyone who walks by to see every single day. And up here is an illustration of one of the amazing predictions that come out of this equation. And that is that even light doesn't travel on straight paths. Okay? Light gets bent. The same way the apple falls along this curved space-time, light now just goes as straight of a line as it can, but the space-time is curved, so it has to bend with it. And one of the effects is this. This is supposed to be the Earth. And then up here is a very bright source of light. Could be a star, could be a galaxy, could be something even brighter than a galaxy, all right? And then you have this ball here is supposed to be some mass. On this picture, I think it's meant to be just the sun, but it could be any other mass that's in between that source of light and us. And if that mass is heavy enough, the light sort of bends in this kind of way. It would normally go at the dotted lines if it weren't bent, but because it is bent, it goes on these lines. And so what we see, instead of seeing the thing appear here, we sort of see the same object coming, once on this path of light and once on that path of light. And of course, the same thing is sort of 3-dimensional. So what you would really see is a ring of light. Einstein had never seen such a thing in his whole life, but we now see those things in the universe, and we call them Einstein rings. So here's exactly what I just described. This blob here, the orange blob, is a big, round galaxy. Now, it's a massive object in the universe, billions of stars in there. And behind it, very far behind it, is another big galaxy that's blue. And one step back, that blue galaxy would only be a tiny speck in this picture, but because of that bending effect, it gets bent all around. Okay? That's a nice little visualization of that.
Emission from the distant galaxy, correct?
Yes, about.
When try to pass close by the bright galaxy, the light bends.
Absolutely. In principle, it's also possible that the ray of light comes straight to you, but that would be, shielded by the light of that galaxy. Wouldn't be visible. So you see the light that's going around, exactly. Now, here is a cool question. Since we now know that light can be bent if you have mass, a lot of mass, is it possible to have an object, a planet or something like that, and a source of light, and that object has so much gravity or so much bending of space-time that the light would simply fall back on it, would never be able to escape. Okay? And so we can take those equations of Einstein and see if that's possible. And the answer is yes, it's possible. And what that would look like is this sort of thing that we call a black hole. Because the answer is you can only do that if you have a hole in the space-time sheet. And that's possible in those equations. Okay, it's a hole that's infinitely deep. Okay, it's called a black hole because, well, it's black because no light can escape, so you wouldn't be able to see anything. And it's a hole because it's a hole in space-time. Right? Yeah, physicists choose simple names. You know, we call it black hole because it's a black hole. Or we say the Big Bang because it's a big bang. I can't blame us for that. Now, the question is, how much, can you actually make such an object? You know, just because the equations tell you it could in principle be there, that doesn't mean the thing exists. And so you could ask, for instance, the question, if you had the entire mass of the Earth, how would you have to reshape it in order to be such a black hole? And the answer is ridiculous. You would have to compress the entire Earth down to the size of a squash ball. If you can do that, you got yourself a black hole. But that thing would now be the mass of the entire Earth. And if I take, you know, a speck off that I can't even see, that would be the entire Mount Everest massive mass. If you can do that, you got yourself a black hole, okay? 2 centimeters roughly in diameter. Turns out that the universe probably cannot do that. We have never seen a 2 centimeter sized thing with the mass of the Earth. And we don't know of any physical process that would possibly compress the Earth down to that small volume. But it gets a little bit better when you have more mass. For instance, if you have the entire sun, you only have to compress the sun roughly to a diameter from here to the other end of King's Park. Now, still very, very small for something as massive as the sun, but the sun is only about 100 times larger in diameter than the Earth. So if you think about this, the density wouldn't be as crazy as it would be for the Earth. And if you take 10 suns or 1 million suns, well, then it gets more and more feasible that you can actually reach those sort of densities. Now, there is tons of evidence for those black holes to actually exist in the universe. And I just want to give you this one. There's a massive one right in the center of the Milky Way. And we knew that sort of for a long time, because when you zoom in with big telescopes in the center of the Milky Way, this is sort of how you can see the Milky Way from the Australian outback, by the way. Take a good telescope, zoom in there, and then where the stars appear the densest, you use an X-ray telescope. Okay? The same sort of machine that detects your broken teeth. That one will find a little speck of X-ray emission right from that center, from an extremely compact region. And we're pretty sure that that's a black hole. And I'll explain you later how a black hole can possibly emit X-rays. Now, the last 20 years for astrophysics have been a lot about zooming into that central region and looking at how the very central stars in the Milky Way move. And these are, the actual tracks of those stars, and that X is the position of the X-ray source. And what you find is that all those stars go around that center on sort of elliptical orbits. And they do so fast. In astronomy, it takes millions of years for anything to change. But here, in 10, 20 years, you see those things do an entire orbit. And they all move on an orbit as if there was a mass in there of 4 million solar masses. Okay? Every single star gives you the exact same answer. 4 million solar masses. The only way, this is about the size of the solar system, the only way you can compress in there 4 million solar masses is by forming a black hole. If you put that much mass into that space, you will get a black hole. Okay? This was awarded the Nobel Prize half a year ago, actually, to German Rainer Genzel and American Andrea Ghez for this particular work. So now that we know those black holes, they definitely exist. There's tons of other evidence. Let's just quickly look a little bit about how they work. So here's your black hole. And here are a bunch of light rays that are coming. And you see that the light rays, they want to go past the black hole, but they get pulled into it, and they land right in the black hole. You have to be pretty far away from the black hole to just swing around and then get back to where you came from, more or less. And now, you know, this black hole is a dangerous place to be, but don't think that it's a good place to be here, even outside the black hole. It is, as a matter of fact, we call this the event horizon, where no light can escape anymore. But the entire zone inside this blue circle is highly dangerous, in the sense that you cannot orbit the black hole in there anymore. If you are in an orbit in there, you will eventually fall into the black hole. With a very small probability, you will get ejected to infinity, okay, back to where you came from. Just to give you a bit of a picture of how I mean this is, we call this the plunging region. You plunge down into the black hole. And a good analogy is a lake where the water falls down from. This part where the water shoots down, that's what we call the plunging region. Okay? Basically, once you are in there, you get smashed down. Okay? It's very, very hard to escape, but you see all that dust of water here. So there's the occasional water particle that gets ejected up. So it's not a given that you necessarily go down, but it's almost certain, and that's what the plunging region means. It's not a good place to be, and you really want to be up in the lake, and that's the region around here where you can still, you know, normally fly a spaceship that has an unbelievably strong engine and so on. You could get away from the black hole. Down here, you still could, but you couldn't place yourself on an orbit without constantly using the thrusters. Then around the black hole is this ring called the photon ring. That's where if you want to circle around the black hole there, you need to be at the speed of light. It's not a stable orbit. You will plunge into the black hole or get ejected, but even if you try to be on that unstable orbit, you have to be at the speed of light. That's why light often sort of settles there before it falls into the black hole. And then right in the center of the black hole is this thing called the singularity. Basically what that means is our equations describing the black hole completely explode. Okay? We do not understand what's happening there. That's very indicative of some sort of new physics taking place. And for the proof that there is always such a singularity in black holes, Roger Penrose, a British mathematician, won the Nobel Prize as well. So loads of Nobel Prizes around black holes, and I've only spoken to you about half of them. Now, because black holes act like these vacuum cleaners that attract stuff, they often find themselves surrounded by gas. Gas that's just lying around in the universe gets close to the black hole, and because it's got some sort of rotation with it, it will start spiraling around the black hole, and because the gas will sort of collide with itself, it heats up, and so every now and then you see these hot flashes of light, and that's the X-rays that we see very often coming from these black holes, okay? So we don't actually see the X-rays coming out of the black hole, but from very close to the black hole.
X-rays is from the gas emission.
Yes, that's right. That is the potential energy that you get as the stuff falls in. The same way you can make electricity of the water that falls down, you get X-rays of the stuff that falls down into the black hole.
The only source of X-ray in the galaxy?
No, absolutely not.
How do we know that this is from around the black hole?
Because of all this other evidence, because you see the stellar orbits.
You have some other evidence, you put them together?
Absolutely. And it's spot on at the center. That's also very sus. Now, normally we don't look at black holes exactly face on. We look at them at some angle. So if we were to look at this same disk from some angle, so we're now spinning it around 90 degrees, what's happening is you don't just see a flat disk from the edge, but you sort of see light up here and light down there, and that's light that's bending around the black hole. So this is a view on the top of the disk behind the black hole. The light has been bent around towards you. And this is a view of the bottom of the same disk. Okay? This same disk, one seen from the top and one's from the bottom. That's what these things look like. And yes, you see here nicely your innermost stable orbit. That's where inside you have the plunging region. Here you see your photon sphere where you have to be at the speed of light, so light is there. And then you get into the event horizon of the black hole. Now, is borderline possible to take a picture of this, but only just, and only in one single case so far. This is a massive galaxy, the most massive galaxy in the local universe, the Virgo A galaxy. And we're pretty sure that in there must be an unbelievably big black hole, 1,000 times more massive than the one in the Milky Way. And we know that because we see jets coming out of that black hole, and we understand that they must be linked to a black hole. So what happened is people have linked up telescopes all around the planet and looked at that particular point where we think must be the black hole to try and see this little disk of stuff that surrounds the black hole. So let me try to zoom into here. This is now a stack of different images from different telescopes. And you see here this jet that's coming out of the center of the galaxy. As you zoom in with radio telescopes, you see that jet going more and more right to the center. And better and better images and so on. And eventually we see this picture. Okay? That's been in the news, I think, a year or two ago. It was the big thing. Black hole has been seen directly for the first time. It's a little bit hard to know how to interpret this picture, but I now move back into the previous one. So what you have to imagine is a blurred image of this. Okay? That's what the media was throwing at you a couple of years ago. All right, now let's come to this final journey where we actually travel ourselves to a black hole. And just before doing so, I have to explain you this thing. Quick drop of wine. Not only do black holes have a lot of gravity, but the gravity increases quite quickly as you get closer to the black hole. And so, say if you fall towards a black hole, your feet down towards the black hole, then the gravity at your feet is a little bit stronger than at your head, which means that your feet are falling faster than your head. That's not a good situation to be in. And it can be first maybe a little bit comfortable, but after a while, you feel that there's a real stretch in your body. And it gets worse and worse and worse and doesn't stop. And eventually, the forces of that stretch will become stronger than the forces that hold the molecules of your body together. And so you will snap. So you're now two pieces going towards the black hole. And then those pieces will undergo the same process and become 4 and then 8 and so on. And at the same time, the black hole is, those lines are converging, so you get pressed together as well. So not only do you get pieced like this, but you get pushed together like that. And that process, believe it or not, physicists call spaghettification. Okay? You become a spaghetti of atoms going into that black hole. Now, that happens very quickly when you approach a small black hole. If we had something like this, the Earth as a black hole, it would happen well outside the event horizon. But if you go into a very massive black hole, like the one in the center of the Milky Way, then this spaghettification only happens inside the event horizon. So if you ever choose to die by falling into a black hole, pick a big one. So at least you get to see what's inside the event horizon. Now, we've spoken right at the beginning of the talk that relativity is such that everything in physics depends on who is observing, what's the motion of the observer. So let's first look at what falling into a black hole looks like if you are in the spaceship hovering a long distance from the black hole, and you have just sent your mate, and she's now going down into the black hole. And what will happen is a really funny thing. Just like in special relativity, time slowed down as somebody was moving really fast. Time here slows down as the gravity becomes very strong. And so you see that astronaut falling more slowly and slowly, even though in her frame, she's accelerating. You see her going slower and slower, and eventually she will freeze just on the horizon of that black hole. And because of that slowdown of time, also her light will change its color. It will become red and eventually vanish altogether. That's what we saw there. Just falling in, turning red and smaller, and eventually disappear. And even if we could still see her in some radio waves or so, we would basically see her freeze on the horizon for thousands, potentially millions of years. And then the black hole will probably bubble up as she becomes, her mass on the horizon becomes relevant and so on, and then the two merge. Now, for her, the story looks very, very different. She is now in this position. Okay, so I'm showing you a movie. It's actually moving, just before I let it go. This is looking down. When I mean down, I always mean down to the black hole, because that's how you define down, isn't it? Down is where the gravity points. We would always call this direction down. It is the same on a black hole. You would naturally feel that where the black hole is, that is down. And the black hole is now, just a small distance below her feet. And this is when she looks up, what she sees, all right? So let's go for this. And you see nothing on the right, but on the left, you see those stars starting to move a bit, okay, and more. And you see those funny arcs here and there. These are now images of the background sources that get bent around. Same way the light got bent around in those Einstein rings, except it doesn't stop, and the rings become larger and larger and larger, and eventually you won't see anything down anymore, and now the other image is starting to move. Because more and more, as you don't see what's down anymore, more and more the light wraps around you, and so the entire universe comes up on your sides. And the light is getting very blue now, because you're so close to the black hole that as the light from the rest of the universe falls towards that black hole, it gains in energy, and so it becomes bluer. And as we continue this, now the entire galaxy is now visible as a ring, and the entire universe goes basically into a point above you. And as it concentrates in this point, the time of the rest of the universe speeds up. The same way the outside observer saw her freeze on the horizon, she now sees the universe accelerate. And if she has a good enough telescope to look back to us, she will actually see at this speed the Earth going around the sun, and see the years and the thousands of years elapse while she is still alive. I mean, that's amazing. That's actual physics. She would see that. She would have absolutely no chance to ever go back and tell us, but that's what she really would see. And then she crosses the horizon and almost certainly would keep seeing this for a while until hitting the singularity, where, according to the general theory of relativity, time and space simply end. Okay? And we know that those theories can't be quite right because they don't map up with quantum theory and so on. It's the end of our knowledge, really. And this is sort of the final view as you fall into the black hole. And because really it's also the frontiers of our knowledge, I'd just like to quote Neil deGrasse Tyson, this great American science communicator, who said, one of the great traps in this world is knowing enough about a subject to think that you are right, but not knowing enough to know that you are wrong. Thank you very much.